Welcome back to the deep dive. Today, we're taking you kind of behind the scenes into the actual infrastructure that powers modern science.
Yeah, the hardware.
Exactly.
Yeah.
Our mission is to understand the technology that acts as the foundation for groundbreaking analytical chemistry research. We're talking about the Specialized Instrumental Facility.
hmm And when we look at advanced places, like the National Center of Excellence in Analytical Chemistry, NCEAC, we're really looking at that essential bridge. It connects theoretical science to, well, practical, real-world results.
That's really key, isn't it? These instruments, they aren't just, expensive boxes. Our source material literally calls them extensions of the researcher.
That's a good way to put it.
They're the tools letting scientists grab onto these invisible chemical things, a tiny pollutant maybe, or a reaction that happens in a flash, and turn it into something solid, something measurable, precise, and reproducible.
Precisely.
Yeah.
So, if you, the listener, are maybe developing a new kind of battery or trying to purify a really critical drug compound or even tracking down where some environmental contamination is coming from,
Right.
the answer really hinges entirely on getting precise measurements. And that comes from these 9 core instruments we're looking at today.
Okay, so let's walk through them. We're going to see how this technical foundation actually translates into, real-world impact, both in industry and academia. Let's start with the core, spectroscopy. The language of light, basically.
Yeah, spectroscopy is fundamental. It helps us figure out 2 main things, and quickly,
Yeah.
what a material actually is and how much of it is there.
And the first tool for that, the most accessible one, is the UV visible spectrophotometer.
UV-vis, right?
UV-vis, yeah. What's its superpower?
Speed
Yeah.
and reliability. UV-Vi measures how compounds absorb light, specifically UV invisible light,
Okay.
and the amount of light they absorb. That's directly related to the concentration, how much stuff is in the sample. It's just
Yeah.
incredibly fast.
So if a scientist needs a quick purity check on a batch, or maybe wants to watch a reaction happen in real time, this is the go-to workhorse.
Absolutely. It gives you that immediate basic data, essential for everything from simple quality control up to monitoring reaction kinetics, how fast chemical A turns into chemical B.
Gotcha. Now, UVVs tells us how much, but what if we need the what? The actual unique structure of the molecule.
Right.
That's where Fourier transform infrared spectroscopy comes in, FTIR. I like the analogy that it's the molecule's fingerprint detector.
Oh, it really is the fingerprint. FTIR works because infrared light makes molecules vibrate in very specific ways. Think stretching, bending of the chemical bonds. And every functional group, like an OH group or a carbon chain, has its own unique vibration pattern. That gives you a totally unique spectrum.
And because that unique IR signature tells you exactly which functional groups are there, you know what kind of molecule you're dealing with.
Exactly. And that's structural insight. Its applications are just immense. It's crucial for polymer characterizations, defining the makeup of plastics, composites, and it's really the main way labs identify unknown contaminants in a sample.
Okay, so identity and concentration covered. But let's switch gears completely. Sometimes a material's function isn't about its bonds, but its skin, its surface area. Why do we need a special tool like the base surface area analyzer for that?
This is critical, especially when you get into cutting-edge material science. Like, imagine trying to filter water really effectively or maybe create a super efficient catalyst.
Right.
The chemical action doesn't happen deep inside the material. It happens right there on the surface. So you often need materials that maximize that available surface.
So the BT instrument measures this by figuring out exactly how much gas a material can physically absorb, like stick to its surface.
That's the core idea, yes. It tells us about the material's porosity, its roughness, the total accessible area. And this insight is just vital for designing better catalysts, engineering sophisticated nanomaterials, or even understanding how things like activated carbon clean up pollutants. If you want faster reactions or better filters, you really need the BET.
Okay, that connects function back to the environment. Now, let's shift from light and surface to instruments dealing with electrical power and really extreme precision for elements, starting with the Potentiostat, controls the interaction between material and voltage.
You can think of the Potentiostat as the tool that lets chemists run these incredibly precise, kind of simulated stress tests. It controls the voltage across an electrochemical cell while measuring the current that results.
Why is controlling that voltage so critical?
Well, it's the absolute foundation of electrochemistry. If you're designing new batteries or trying to model how steel might corrode, or maybe developing sensitive biosensors that work off a tiny electrical signal change. You have to understand precisely how your material behaves under that voltage stress. The Potentiostat gives you the stable, controlled environment you need to figure that out.
Makes sense. Moving to elemental analysis then, we hit what you might call the analytical heavy hitters. Two systems focusing on metals, trace elements, starting with the complex-sounding but powerful ICP-OES, inductively coupled plasma optical emission spectroscopy.
Yeah, the name is a bit of a mouthful, isn't it? But the concept is pretty incredible. This machine generates plasma.
Plasma, like superheated gas.
Exactly. A state of matter way, way hotter than the sun's surface. And it uses this plasma to completely atomize the sample, break it down into individual atoms.
Whoa, wait, it basically incinerates the sample. Why do that?
That's the key. By turning the sample into its component atoms at that crazy temperature, those atoms emit light at very specific wavelengths. The instrument then measures that emitted light. And because every element has its own unique color signature when it's heated up like that, we can tell exactly what elements are present and in what quantity.
So the ICP-OES is like the multi-element expert. It can measure dozens of elements at the same time with incredible accuracy, down to parts per billion even.
That's right. It's the real powerhouse for high-stakes, high-precision work. Think global environmental monitoring, where tiny traces of heavy metals are critical, or high-end metallurgy, pharmaceutical QC, where you absolutely cannot miss an impurity.
Okay, so if ICP-OES is that powerful multi-element specialist, why would a lab still need or use the atomic absorption spectrophotometer, the AAS?
That's a fantastic question. It gets right to the heart of experimental trade-offs. The AS also detects metals, but it works differently. Instead of measuring light emitted by hot atoms.
It measures light absorbed.
Exactly, absorbed by atoms. And critically, it usually just looks for one element at a time.
So it's less comprehensive. But what's the advantage then? What does it offer that the ICP doesn't?
Speed and, frankly, cost efficiency for specific tasks. If you know you only need to check for, say, lead in drinking water or maybe mercury in soil samples,
Right.
the AAS is quicker, it's much cheaper to run per sample, and it's highly reliable for that specific job. It's really the essential high-volume workhorse for routine quality control in manufacturing, water testing, industrial monitoring, places where budget and speed often matter a lot.
That makes perfect sense. ICP-OES for the deep dive on unknowns, AAS for focused repeated testing. Got it. Okay, let's talk complexity. Most real-world samples aren't neat, right? They're mixtures.
Almost always.
So we need pools to separate out that complexity, and that means chromatography.
Chromatography is often the necessary first step for almost all advanced analysis. It basically takes a complex chemical soup and separates it into individual ingredients so you can identify and quantify them one by one.
Starting with the volatile stuff, things that easily evaporate. We use gas chromatography, GC, for that.
GC specializes in things you can heat up and turn into a gas without them falling apart. It pushes the sample through a long, thin column, and the different components separate based on how they interact with the column material and their own physical properties, like boiling point.
Sounds critical for detecting things we might, well, smell or inhale.
Oh, absolutely.
Yeah.
It's used constantly in forensic science analyzing trace evidence, in the petrochemical industry for grading fuels, and really critically in air quality monitoring to check for atmospheric pollutants, volatile organic compounds, things like that.
But we know not everything turns into a gas easily. Lots of biological stuff, complex polymers, drug molecules, they just won't vaporize nicely.
Right, they degrade or just don't cooperate.
So how do we separate those? That's where liquid chromatography comes in, HPLC or LC.
Exactly. LC uses a liquid solvent, the mobile phase, to carry the sample through the separation column instead of a gas. It's the fundamental tool for handling complex mixtures that are already in liquid form or can be dissolved.
And its applications seem truly foundational for, like, public health and safety.
Oh, they really are. LC is basically the backbone of pharmaceutical research. It ensures the precision, the purity, the exact dose of active drug compounds.
Wow.
It's vital in biological studies,
Yeah.
analyzing proteins, metabolites, and essential for food analysis, detecting additives, contaminants. If you took any medication today, chances are liquid chromatography was involved in checking its quality.
Okay. Finally, we get to the frontier where chemistry meets, well, physical creation, the electrospinning unit. This sounds like where chemistry meets engineering to actually build things.
This is definitely the material science playground, yeah.
Huh.
The electrospinning unit uses high-voltage electricity to draw out a polymer solution or melt into incredibly fine threads, nanofibers, often hundreds of times thinner than a human hair.
Hold on, how does high voltage turn a liquid into a microscopic fiber? Can you simplify that a bit?
Yeah, sure. Essentially, you apply a really strong electric field to a droplet of polymer solution at the tip of a needle. This electrical force overcomes the liquid's surface tension, stretching it out. As it travels across a gap towards a collector plate, the solvent evaporates super fast, and this stream whips around, solidifying into this continuous, ultrafine fiber.
Like pulling taffy with electricity.
Kind of, yeah.
Yeah.
A very high-tech version of it. And the result is this non-woven mat of nanoscale fibers, highly porous.
And these tiny engineered fibers must have huge implications.
Well, they do, because they have an enormous surface area compared to their volume. Remember our chat about the bead analyzer? They're revolutionary.
What connects back?
Yep. They're used to make advanced high-efficiency filters, to develop complex drug delivery systems where you want controlled release. And they form the basis of next-gen wearable tech, smart sensors. It's a direct route from designing a molecule to making an innovative physical product.
So, wow. We've covered 9 specialized instruments, everything from the basic UV-vis check all the way to the electrospinning unit making new materials. It's quite a catalog. But let's bring it together. What's the overarching impact, the measurable result of having all this capability in one place?
The collected so what, really, is research transformation across massive sectors. Because these specific tools are available, researchers can actually do things that directly benefit society.
We're talking concrete projects here, not just theory.
Absolutely. This facility supports everything from very local work like detecting tiny amounts of pollutants in nearby rivers or testing the strength of new composite materials, all the way to global challenges.
Right.
Things like developing better electrode materials for the next generation of batteries.
Right.
Or rigorously testing the quality and safety of pharmaceuticals that are going to be sold internationally.
And the course has mentioned that this infrastructure isn't just for academic papers, it directly helps innovation through collaboration.
That's a key metric of success, definitely. You see the evidence in strong collaborations with various industries, which leads to externally funded research projects. And ultimately, a significant number of high-impact international publications. This setup doesn't just support learning. It actively drives the engine of scientific innovation that pushes technology forward.
That's a really inspiring look at the tech behind the research, supporting students in crucial industry work. Thanks for making that technical maze feel, well, pretty navigable.
My pleasure. And, as we wrap up, I want to leave you with one final practical thought. It relates directly to the choices researchers face every single day.
Okay.
We spent some time contrasting those two elemental analysis tools, right? The atomic absorption spectrophotometer, COSAC, versus the inductively coupled plasma, ICP-OES, incredible multi-element accuracy, but slower, more expensive.
Yeah, the classic tension, speed, budget, precision.
It is. So here's the question maybe for you to think about. When a team is designing a big, long-term monitoring project, maybe tracking new contaminants in a huge water supply, or ensuring the safety of a complex food chain, how should they balance that? How do you balance the need for high-volume, affordable screening like you get with AS against the absolute ethical and scientific need for the highest possible precision, which comes from powerful, maybe slower tools like ICP-OES? Where do you draw the line?
Wow.
Because that practical choice often defines the scope, the limits of what we can know scientifically, and ultimately how quickly we can act to ensure public safety.
A fascinating problem to end on. Defining the limits of what we know versus what we can perhaps afford to know. Until next time, keep digging deeper into the science behind the scenes.